Hello friends. So, continuing our discussion on the interpolation functions for two dimensional domains or the finite elements, we were discussing about the requirements of the interpolation functions for two dimensional domains and how to do that. So, we discussed this interpolation complete basic requirements of the polynomial approximation for the convergence of finite element solution are capability to represent rigid body motion and the capability to represent constant strain states. Now, what do we mean by this? We have been talking about this earlier also. So, the most elementary polynomial in two dimensions which satisfies these two requirements is first degree polynomial, that is a 0 plus a 1 x plus a 2 y. We use the similar kind of expression for deriving the interpolation functions for triangular element, 3 noded triangular element, right. So, there are 3 unknown parameters a 0, a 1, a 2. So, we call them alpha I, beta I, gamma I in case of interpolation function for node I, and obviously these 3 parameters can be evaluated if I have 3 constraints to define these parameters, and those 3 constraints are given by the interpolation condition that n I should be equal to 0 at n j at x j y j and x k y k, and it should evaluate to unity at x I y I, right. So, that is the interpolation function itself. Now, if I wish to go to higher order element, higher order approximation. So, this is the first degree polynomial. So, linear approximation. So, the displacement variation of u and v within the element are going to be limited to first degree polynomial. Now, accuracy of course depends on the degree of approximation. So, if I want to converge quickly, then I need to incorporate higher degree terms in the approximation. So, next higher degree term which is complete and which may constitute the requirement is a second degree polynomial. So, I need to add second degree terms to these first degree terms that are already existing. So, what are the second degree terms? I need to include x square term, I need to include y square term, and I also need to include cross product x y term. X y is also a second degree term from the second degree polynomial. So, a complete second degree complete polynomial is given by 6 terms with 6 unknown coefficients, right. These coefficients, in order to evaluate these 6 coefficients, I need to know constraints. I need to have 6 independent constraints. So, for which will allow me to evaluate these 6 unknown coefficients for the approximation. So, we can go in the similar fashion and derive it what we did for the triangular element, for 3 node triangular element, but we will see there are more systematic ways of doing that. So, but for the existence of a valid approximation, it is essential to ensure that the number of independent terms in the polynomial approximation is equal to the number of nodes in the element, because that is what will give us the basic constraints on the variation, that interpolation condition, right. So, the terms of the polynomial approximation should be chosen such that all lower order terms up to the required degree of complete polynomial, including the constant term, are included. So, all lower order terms. So, it means if I want to include second degree complete, because the rate of convergence would be defined by what is the complete approximation, degree of complete approximation what is the degree of polynomial which is complete in the approximate solution that we are constructing. So, if it is a second degree complete polynomial, then I need to have not just all second order terms, second degree polynomial terms, I also need to include all the first degree polynomial terms, the linear terms, and also the constant term in the approximation, and then count how many terms are there and how many constant arbitrary coefficients are there, and then I need to have those many nodes in the interpolation in the element suitably placed, which will allow me to evaluate those or define the suitable approximation. Now, I said suitable location of those nodes, because it is not they cannot, I mean, nodes cannot be thrown around or in arbitrary fashion. There is a method to that, and sometimes a few higher order polynomial terms may also have to be included in approximation, so as to make the number of independent terms equal to the number of nodes in the element. For example, a particular example that I can cite right away is the 4 node rectangle, right. So, there are 4 nodes in this element. So, I can label them as 1, 2, 3, 4, right. So, what are the polynomial terms that I will have? So, if I wish to find what is the approximation within this element u, then it will be A0 constant term, x linear term in x, linear term in y. So, these complete the three terms, but the number of constant the number of these coefficients A0, A1, A2 and A3. So, I need to have 4 coefficients, because there are 4 nodes. So, in order to have a one to one mapping, that this approximation that I construct is unique approximation defined by the nodes defined by the over this particular element, rectangular element defined by these 4 nodes 1, 2, 3, 4 of the coordinates x 1 y 1, x 2 y 2, x 3 y 3 and x 4 y 4. So, that unique approximation can be constructed only when I have this 4th term present in this approximation. Now, what this 4th term should be? We know that it should be as small as possible, because higher order polynomial, they can actually construct create lot of problems, as we saw in the approximation interpolation function approximation, interpolation approximation of the Runge's function in while our discussion on interpolation theory. So, high order high degree polynomial can have very wild fluctuations. So, we should have as low degree as possible. So, the lowest degree additional would be second degree. So, possible candidates here are x square, x y and y square. So, which of these 3 should be included? Of course, only one can be included. Another option would be to add all of them together, x square plus y, x y plus y square, and then put them in this multiplied by A3 whatever, or I can that would be lead to another problem that we will see later. But what do we need to include here? So, the possibilities are A3 x square or A3 x y or A3 y square. So, whatever we choose, this term is spurious term. We call this spurious term because this term comes from second degree polynomial, and second degree polynomial is not complete here. So, the convergence will be defined by the highest degree of complete polynomial, that is 1 in this case. So, this is first degree complete, 4 node rectangle, approximation over 4 node rectangle is complete up to first degree. So, this second degree term is anyway spurious. So, irrespective of whatever we choose, that is only to meet the requirement that I need to have a fourth term here, because otherwise I will not be able to ensure unique approximation, polynomial approximation, unique definition over these 4 nodes, right. And the guidance is, let me just say, if we define this term. So, let us say I use x square, let us say I prefer to use x square. So, I define x y as a 0 plus a 1 x plus a 2 y plus a 3 x square. Fine, nothing seems pretty fine. I mean, there is no this term is anyway not contributing to convergence of the results. So, this is spurious term, I can probably not attach too much importance to this. But what happens is the choice of frame of reference, I mean this will be encoded in your finite element formulation x and y. These are based on certain orientation of frame of reference x and y. So, I choose x to be here and y to be here. But if somebody uses this element which has been formulated and all the element coefficient matrix and everything, all definitions are there. So, after that all that needs to be done is choose this element and feed the coordinates of these 4 nodes, and that is all. Rest of the things are already computed and coded in the program, the software, finite element engine. So, none of these developments have to be done again and again. So, this is already done and dusted while coding it into the finite element engine. So, what happens is this is based on this assumption of x and y, choice of frame of reference. What happens if somebody else comes and chooses to define x as this and positive direction of x and y like this, or more weirdly I would say it chooses to define, the person chooses to define y as x and x coordinate like this. Now, and the person is completely oblivious, the coordinates in this new frame of reference, it will have some coordinates, and the person the user will just feed these coordinates in this equation and everything will be done accordingly. Now, what is the problem here? Up to these it is symmetric in x and y, up to this term the approximation is symmetric in x and y. So, it really is invariant, whichever way you orient your axis, the results are not going to be affected. But this term here has a preferential direction towards x, the approximation depends on where x is marked. So, in this case if this direction is marked as y, then and this direction is marked as x, then in this particular case the variation is being considered is in this direction, whereas what the formulation has been done is with x pointing in this direction, right. So, this we call this as a preferential direction. So, x direction is more heavily loaded and it has the results would differ from user to user depending on how the user chooses to define the frame of reference, because the frame of reference, choice of frame of reference is entirely arbitrary. It is entirely up to the user which way the user chooses to orient the axis. I can as well choose to orient the axis along like this. The result should not change. Result should not depend, my analysis result should not depend on this choice of frame of reference, and that can only happen when this approximation that I consider, they are symmetric with respect to the coordinate directions, and when that happens, then the choice of frame of reference will not have any influence, and this is what we call as geometric isotropy. So, this spurious term, that is few higher order polynomial terms, will also have to be included in the approximation, so as to make the number of independent terms equal to the number of nodes in the element. So, just as we needed fourth node, and therefore, symmetric term is x y. So, the fourth term should be not a 3 x square or a 3 y square, it should be a 3 x y, right. This is now symmetric in x and y. Now, we may also say why not a 3 x square plus y square, this is also symmetric in x and y, is not it. So, the problem is this is, although all of them are second degree polynomial term, but this is product of two first degree polynomials, x is in linear, y is in linear, and this is, both of them are quadratic in each in their own right. So, this is preferable, and this will also satisfy other conditions that we will see very soon, right. So, general rule is choose the terms which are symmetrically placed in Pascal triangle and which are closer to the center line of the Pascal triangle. So, we do that. So, in such cases, the extraneous terms that we choose. So, the fourth term is the extra term. So, we choose this extraneous terms, they are selected from the Pascal triangle which are placed symmetrically. So, Pascal triangle, symmetric position in the Pascal triangle, we pick up those terms. So, this requirement of symmetric terms, symmetrically placed terms in Pascal triangle is necessary to enforce geometric isotropy. That is what we discussed a little while back. Avoid having preferential direction too heavy in one particular coordinate direction. So, to have enforced geometric and isotropy in the approximation of primary variables and refers to the chosen polynomial approximation not being extra sensitive to the user specified orientation of the frame of reference. So, the analysis results should not change by the user's choice of frame of reference. So, users can choose whatever whichever way the frame of reference needs to be oriented. The analysis results should remain same, should not be dependent on that. So, what does Pascal triangle look like, which can help us address this concern? So, this is a simple Pascal triangle geometry that you can see, and you can as well keep on expanding, right. I stopped at the fourth degree polynomial because that is all I could fit in this space, but that is sufficient to explain the concept. So, it starts with 1, that is the constant term, then 2 linear terms x y. So, this is the center line of the Pascal triangle what I mentioned. Then next is x square, that is quadratic, x y product of these linear terms, and then y square. Then next third degree polynomial cubic. So, that would be x cube, then x square y, and then x y square, and then y cube, right. So, you can see this as x y square and y x square y. So, these are the product of lower order terms. So, this is a cubic polynomial. So, cubic polynomial will have 4 independent coefficients. Quartic polynomial will have 5 independent coefficients, and again those 5 terms would be x raised to the power 4, x cube y, x square y square, x y cube, and y 4 y raised to the power 4. And similarly, you can expand this polynomial, but for finite element approximation we rarely I mean, of course, some of the terms can come from higher order term, but as far as complete polynomial is concerned, we rarely go beyond quadratic second degree complete polynomial. So, the approximation terms, of course, some of the spurious higher order terms would be there in order to ensure the constraint requirement, but we rarely make use of finite elements which are based on polynomials complete beyond second degree, right. So, when we say it is complete in up to second degree, I mean I need to have this constant term, I need to have this linear term, I need to have this linear term, and then I need to have this x square, x y and y square, all 3 quadratic terms. So, when I have all these 3 quadratic terms in the approximation is capable of accounting for all these 6 terms, right, starting from constant to quadratic, then I can say that the approximation is complete up to quadratic, right, and then the whatever extra is there, that is the spurious term. Those are the spurious terms and they do not contribute towards the convergence properties, but they do contribute towards establishing the unique definition of the polynomial approximation based on the number of nodes that are there in the element, right. And we will see how the these basic considerations that we have discussed, they translate into design of finite elements, particular finite elements. We will start with triangle family of finite elements, that is the simplest finite element in 2 dimensions, and then we will see rectangular family of finite elements, and then see how these are what is involved in constructing finite element mesh. How do we decompose the problem into using finite element mesh and then solve this problem using these elements, right. So, we will start with triangular family definition and properties in our next lecture. Thank you.